good time of day to you whenever you're watching this. Let's have a recap of what we did in class, starting with Newton's first law. So we talked about how forces are pushes or pulls, that there are two types of forces, the long range and the contact force. And we also talked about Newton's first law, which is the so-called law of inertia. Inertia is the intrinsic property of anything, any object that has mass, to keep its state. Hence, an object in motion stays in motion with a constant velocity, not turning, not slowing down, not speeding up. And an object at rest, remaining at rest. So objects tend to want to keep doing what they're doing, either chilling or moving in a straight line at a constant speed. Mathematically, we can express that first law as net force equals 0, then velocity is constant. Wording, unless there is an unbalanced force, unless there's an outside force, an object at rest will remain at rest, an object in motion will remain in motion at a constant velocity. Then, after that, we looked at several examples of when forces were balanced. And we also started with the formula for force of gravity. So remember when you tended to say G was gravity, I was getting a little irritated. The reason for that is acceleration. It is measured in meters per second squared. Therefore, that is not a force. Gravity, however, is a force. It is measured in Newton, and what you can see right here, I'm showing you what is inside a Newton. So it is very important to remember that mass needs to be in kilograms. And if you are given a mass in grams, divided by 1,000, because 1 kilogram is 1,000 grams. So if you have 500 grams, for example, that is 0.5 kilograms. So remember to always switch to kilograms when you're calculating anything. So if we have a person whose mass is 82 kilograms, then what is the force of gravity exerted on it? And what is more, what would be his weight standing on something or sitting on something? That is what a weight is. That is a force that you will apply to anything you stand on, sit on, lie on. In other words, your body is pressing into something with your weight. And that weight usually, but not always, equals to the force of gravity exerted on you by planet Earth, if you are on Earth. Since we're talking about Earth here, 82 kilograms times 9.8, 803.6, so 804 newtons. 3 questions, A, B, and C. We're asked to draw an FBD. Remember, an FBD is a free body diagram, free of everything. We're just concentrating on the object, and we are not concentrating on AP art. If you want to do a stick figure, go for it. Some of you have a beautiful specimen of a stick figure. I'm just going to do a dot to represent a person. And I'm going to show force of gravity downward. You mark it as force of gravity. You can also mark it as mg to remind yourself what the formula is. Either one will go. And then there is a force of air resistance, which is less than force of gravity at the very beginning. Now, the thing with force of air resistance or air drag, it increases with the increase of speed. And because right now, if we look at this, acceleration is downward, and I'm not going to mark it g, because remember, g is the acceleration when there is no air resistance. And because of that acceleration, the speed is going to be increasing, and because the speed is increasing, force of air resistance is increasing. And at some point, force of air resistance is going to be as big as force of gravity. Hence, I'm just going to duplicate this. So there you go. When force of air resistance equals force of gravity, when they balance each other out, there is no acceleration, and terminal velocity takes place. And remember, terminal is not because if you hit the ground you'll die. It's terminal because it cannot get any higher than that. That is as fast as the given object, which is a human body, can be falling at. You can look it up. It depends on the size. Parachute is open, increasing the force of air resistance. And because of that, now that force of air resistance is greater than gravity, acceleration is now upward. And remember, if you're falling down and acceleration is up, that means you're slowing down. There you go. The rest of the examples in this worksheet are on surface. So when we draw a surface picture, we just draw a horizontal line to show us that we're not dealing with an object that is falling through the air or the absence of air. So here we have a 25 kilogram box resting on the table. And because it has mass, it's going to have force of gravity, and the opposing force to force of gravity, we talked about, it's called normal force. Not because it is not abnormal or because it's not weird. Geometrically, the word normal means perpendicular to the surface. So force normal is a reaction to weight. So the box resting on the table is applying its weight to the table, and the table is returning the favor by applying the upward force. And so the two forces, the force of gravity and normal force, are the two forces applied to the box. Force of gravity equals normal force because they are balancing each other out, and we're using the formula 25 times 9.8. That would be 245. And 245 what? 245 newtons, because that's the unit of force. In example 4, the same box, it has a 25 newton force. See how I'm trying to trick you? 25 kilograms, 25 newtons, it's a different thing. 25 newtons is a force of pull, and I'm going to show it to the right. It's not moving. Explain why the box is not moving. When does an object at rest remain at rest? If net force equals 0. Now what we see here, that net force is not 0. I mean, vertically it is, because vertically these forces equal each other and are opposing each other in direction, so they balance each other out. But force of pull right now is unbalanced. It's unhinged. Nothing is opposing it. So according to what we know, this box should be speeding up like crazy to the right, but it's not. The reason for it must be another force. And that force is force of, you got it, it's a force of friction between the surface and the box. So that force of friction is stopping the box from sliding. And mind you, force of friction is a lazy force. It will only give you as much as it needs to. You pull with 25 newtons, force of friction is giving you counteraction, and therefore your box is not moving anywhere. In problem 5, you have a repeat. You have a force of 290 newtons to the left. The only difference is the direction of forces. So now 74 times 9.8 is force of gravity and normal force. Force of pull and force of friction are both 290. Boom. Everything is balanced, and an object at rest remains at rest. In the next example, we have no pull or push and no friction. It's just sitting. We have a box resting on the scale. So this is the scale applying the force upward, and it reads 147 newtons. The question is, what is the mass of the box? So if force of gravity is 147 newtons, and it equals mass times g, remember how I didn't say mass times gravity, it's mass times g, that is gravity. That is going to be our question mark, so mass is going to be 147 divided by 9.8, which will give us 15 kilograms. The last two examples are getting a little bit trickier because we have different number of forces up and down. So up till now, our downward force of gravity was balanced exactly by the upward force from the scale. In these two examples, we have a little bit of a trick. So I'm going to start with the 45 kilogram suitcase. If it's 45 times 9.8, it's 441 newtons. This is what the scale should be reading if the scale is marked in newtons. But see what is being done. If I draw the free body diagram, this is force of gravity. It's 441 newtons. If we didn't have an interference from the passenger, this would be force normal. However, what we see is that that person is applying a little bit of a push-up. I'm going to mark it a little bit to the side so we can see two separate forces. So this is the force that he is applying upward, and that force, I'm going to label it force of pull, equals 100 newtons. Now see how downward we have 441 and we already have 100, so the normal force provides just the difference, 341 newtons. So normal force plus force of pull equal force of gravity. So therefore force normal is 441 newtons minus 100, and it becomes 341 newtons. So instead of 45 kilograms, if I divide this 341 by 9.8. The mass, the apparent mass, so this is called the apparent weight. And then the apparent mass is about 35 kilograms instead of 45. There's a big difference right there. That's 22 pounds. Now the last example is the opposite. So if here we had the subtraction and normal force being less than the weight or force of gravity. So it's a 5 kilogram melon. 5 times 9.8 is 49 newtons. So we have force of gravity 49 newtons, and the weight should be 49 newtons on the scale. And there we go. There's an extra 20 newtons. So because of those extra 20 newtons, our normal force, or the reading of the scale, is going to be 49 plus 20, 69 newtons. And then 69 newtons divided by 9.8 meters per second squared gets us about 7 kilograms, a little bit more. So something can appear to be lighter and something can appear to be heavier if there's an upward force or a downward force. There's also a case of moving in an elevator, but that will be a totally different story at one of our next lessons. Thank you for watching and hope this was helpful. Keep learning.